Hello everyone, I am Ridwan Shariffdeen. I'll be presenting our work on automated patch transplantation. This work is a collaboration with colleagues from National University of Singapore, Southern University of Science and Technology, China. Our work is inspired by the transplantation process in medical science. Transplantation is a process of transferring living cells, tissues or organs from one part of the body to another part of the body within the same organism or for different organisms. We use the same concepts and principles of the transplantation process in medical science in the context of software engineering. In this process, the donor and the host is the software system, while the donation is a code instead of an organ. We formulate the problem of patch transplantation as follows. Given a pair of programs PA and PB, for which PA is the version of the program that fails for a given failing input TF, and PB is the version of the same program that passes for the failing input. The problem we formulate is, can we extract the patch from PA to PB and transplant it into a similar program PC that can generate a program PD which will pass for the failing test case TF. The necessity of a patch transplantation technique in software engineering is due to the standard procedures of vulnerability disclosures and the publication of patches help malicious users identify the existence of vulnerabilities and target unpatched instances of these vulnerabilities in the wild. A recent study from Iowa State University finds a special class of vulnerabilities called recurring vulnerabilities. Recurring vulnerabilities are similar vulnerabilities that exist in different systems due to three reasons. They either share the same source code, or they share the same set of libraries, or they share a common artifact at a higher level of abstraction such as specification or a protocol. These studies indicate the intertwined relationship between patches and vulnerabilities helps malicious users to identify the existence of vulnerabilities through the publication of patches. And this makes a bigger impact on systems that have recurring vulnerabilities. We implemented our technique in a tool called Patch View, which can automatically extract and transplant the patch to repair another similar vulnerable implementation. The key contribution of this work is to automatically identify the location for the transplantation process. We define a divergent point as a location in the program where the execution trace start to deviate due to the patch. The first step is to collect partial path conditions at each divergent point. A partial path condition is the path condition observed at a midpoint in the trace and is captured by a conjunction of constraints over the input. Partial path condition dominance is a relation defined for two partial path conditions. Given two partial path conditions alpha and gamma, we define the dominance relation for gamma if input bytes in alpha is a subset of the input bytes used in gamma. Consider the example shown in the slide. A is the input bytes used in alpha and B is the set of input bytes used in gamma. A is a subset of B, hence gamma dominates alpha in this context. We use the partial path condition dominance relation to estimate a divergent point from the donor program to the target program. We compute the partial path condition at each of these lines in each program and extract the input bytes that is used in the partial path condition. And using the partial path condition dominance relation, we can find that the line number 7 in PA and line number 10 in PC are estimated divergent points. We now illustrate the transplantation process in PatchView through a real-world application program. The code shown here is a snippet from the OpenJPEG library 1.5.1, which depicts an integer overflow over two variables that is provided by the user and is unsanitized up to this point. The same vulnerability occurs in another library called Jasper and has been fixed by the developers of the Jasper library. We will use this recurring vulnerability to illustrate the transplantation process in PatchWeave. More specifically, the inputs for our transplantation process is a donor program, which is the Jasper library, which has a fix given by the developer, and the target program or the host program is the OpenJPEG library 1.5.1, and we use the same failing test case in the exploit of the CVE 2016-9387. We first verify the existence of the recurring vulnerability in both programs. We provide the failing input to Jasper and observe the signed integer overflow as shown in the slide, and the same input provided to OpenJPEG, and we observe the same signed integer overflow as observed in the slide. The next step is to identify which code needs to be extracted from the donor program for the transplantation process. For this purpose, we concurrently execute the donor program with the failing test input and identify the code that influences the final outcome. Once we identify the code to be extracted from the donor program, the next step is to identify the insertion point in the target program. For this purpose, we will use the partial path condition dominance relationship we defined earlier and estimate a divergent point from the Jasper donor program to the target OpenJPEG program. In this illustration example, we will show a partial path condition obtained at a specific location in Jasper, from which we will extract the input byte that is used for the partial path condition. Similarly, we will iterate through all divergent points in the target program and identify the partial path condition at each divergent point, and similarly extract the input bytes for each partial path condition. For each of the partial path conditions in Jasper and OpenJPEG, we will recursively analyze for the dominance relationship. Once we identify a estimation of the divergent point using the partial path condition dominant relationship, we can estimate a divergent point in OpenJPEG, and using the divergent location we estimated, we can estimate a candidate insertion function, and through the candidate insertion function we can find the insertion location for our patch. Once we identify the insertion location, the next step is to adapt the patch to the target location. We extract the variables in the patch from the donor program and extract the live variables available at the target location, and for each variable we obtain the quantify-free symbolic expression through the concurrent execution we previously conducted. By using an SMT solver, we provide an equivalence check for each of the variables symbolic expression and find a mapping between the donor program and the target program. Using this mapping, we can obtain an adapted patch which matches to the target context. The next step is to recursively identify the missing ingredients for the patch that should be inserted in order for the patch to work. We do this by recursively analyzing the abstract syntax trees of the patch and the target code. First, we identify the missing variables and import them. Then we identify the missing functions that needs to be inserted in order for the patch to work. And then we recursively identify any macro definition that should be inserted. The final adapted patch is shown in the right side of the slide, which includes all the necessary ingredients for the patch to work in the target program. We verify that the transplantation is successful by running the failing test input that was observed to be an error in the program before the transplantation and observe no error after the transplantation. We evaluate our approach using 8 application programs involving 24 fixing tasks. All applications used in our experiments are file processing software. Out of the 24 fixing tasks, 20 of them were successfully transplanted by PatchWeave. In these 20 test cases, PatchWeave was able to identify the first candidate function as the correct location for 11 instances, and 15 of them hit the top 5 selection. In summary, the patch transplantation problem caters to a real-life need of the practice of software security. Due to the publication of security patches, unpatched similar instances be more vulnerable to be targeted by attackers. This work provides a solution to reduce or remove such exposures to vulnerabilities. This is the end of my presentation. Thank you for listening.
Hello everyone, I hope you enjoyed the video presentation from the work on automated patch transplantation. in this blended session, we are collecting this work that has been published in ACM TOSEM, so it's a journal first paper. And here with me, I have two authors, Ridwan, Salihin, Shariffdeen, I hope I pronounced it well. And there is also Shin, Hwei that maybe you cannot see, her camera is not on. And I am asking you to please give your question to Ridwan in the chat. By the way, I made already other session, but I did not present myself in this one. My name is Antonia Bertolino, in case you didn't attend the other session, and I am chairing this blended session. So while people warm up and write down their question in the chat, I will warm the floor, and I will make one or two questions to you, Ridwan. So while I listened to your presentation, I was asking myself that this technique is very nice. So why you restrict only to patch? Maybe because of the local localization of the code that you want to transplant? Could you also try to correct bug taking from a correct program, even if it was not patched before?
Yes, definitely. So if there is a bug that is common in both the programs, which can be a functional bug, and there is a common test case that exercise both the function bugs that can be exercised to the programs, definitely we can apply. But the most common scenario we find if there are two programs, if there is a bug, is certainly a vulnerability, and that is why we focus on security vulnerability, because it was very easy to find such examples that there are two semantically equivalent programs, and there's an exploit that exploit both the programs with the same test case.
Okay,
but definitely if there is also other options, like if you have a test case, not necessarily be a bug per se, but if you have a feature transplantation, also this is, if there is a common scenario which can be verified that the transplantation is working, definitely.
And at a certain point during your presentation, you mentioned that you do this transplantation on looking to similar, I don't remember if you said similar code or similar program. Could you explain a little bit more about how do you decide that something is similar? How do you measure similarity?
Yes, so in this context, similarity is measured if the two programs are behaving semantically the same input we provide. For example, there are many programs that implement the same process or the same protocol, the same standards, and if these are common set of semantic similarities, they not need to be equally semantic to all input. One input that they exercise is semantic equivalence. This is what we call a similarity. So the similarity, we define it as if there is any input that is exercised in the same way in both programs, that is a similarity that we're looking for. So we're looking for any tool in software implementation that implement the same standard or same protocol. That is the high level abstraction that we look at.
But also syntax, right? You need also to look to code for syntax similarity, of course, right? So semantic is on top of syntax.
No, they need not be the same syntax. So, for example, we had an example where two softwares called Jasper Library and OpenJPEG, which they were processing JPEG standard images, and those two doesn't have any similarity with their code bases. They're semantically processing the same image, so the implementation is quite different.
Oh, interesting. Okay. I am still looking in the chat. No question. So everything was clear. Maybe if you could, yes, there is a question. No question is stupid, Alex. You say maybe a stupid question. So which ingredients you need to transplant a patch? Is the patch just a patch file, for instance, taken from a Git commit, or does it need to be annotated further? There is a second question I will read later.
So the patch ingredients at the moment we have implemented as a Git commit. So we need to have the version before the patch and after the patch. So we can extract the patch, and it doesn't need to be annotated. To symbolic execution on concolic execution on both the program and the same input, and extract the exact code that is affecting the patch to work, and then we extract this patch as a transplantation. So annotation can definitely work, so it can help further improve the code that we need to extract and transplant. But at the moment we have automated in a way, so we look at the trace execution and then we extract which code is exactly relevant for the code. So the second question is
if you determine automatically the location at which to apply the patch, or if the user need to make explicitly the request in a certain program location for the patch.
Yeah, so the novelty in this work is that we automatically determine the location that we transplant the patch. So there is no user have to manually specify any location. So since there is a semantic similarity between the two programs, we look at how this patch program has we look at the control flow of the patch program, and then we try to locate the insertion point in the donor program with the similar control flow. I hope that clarifies the question, or if there's any further follow-up, I will be glad to answer.
Yes, and Fahad asked if you measure the similarity at function level or at instruction level, or if one of the two is better than the other.
So like I explained, the similarity between the two programs can be at a high level of abstraction. So it does not need to be syntactically equivalent at the function instruction level. So the programs need to just have the same semantic behavior on the same. So that's the high level abstraction that we have for similarity.
Okay, I saw Alex doing the thumb on, say that your answer before was okay. 1 minute and a half for one more question, maybe. And by the way, Ridwan, when we finish the time, Clouder will disconnect, but you can still enter the discussion room, and the audience can make you directly question in the discussion room.
All right.
Okay, so in case the time finishes before you answer the question from the audience. So in this 1 minute, instead of staying silent, I will make one more general question. So what is the deployment that you think for this tool? Who should be using it? Why, when, where? So who would be the user of this tool for patch transplantation, and when to use it?
Yeah, so definitely the software developers who are keen to, so there's a category of vulnerabilities called recurring vulnerabilities. So these vulnerabilities, so if you have a similar program and there is a vulnerability found in one of the semantically similar program of yours, and this vulnerability could also be exploited in your program. So you need to be aware of it and try to fix it. And if there's already a patch in a similar implementation, the easiest way is to try to extract it and transfer it into your program, so your program is also safe from the same exploitation. So program developers of such libraries and programs which have multiple implementations or competitions per se, or repositories that have cloned on your own, and for example MySQL and MariaDB with example, they have the same code base. So if you find a vulnerability in one of the repositories, it's also possible to find the same vulnerability in the other. So for such instances, it's easy if you have a